Welcome back to our next talk. And here today we have Jaime, who is an electrical engineering turned software dev turned security researcher. And she caught the InfoSec bug through playing CTFs and now works at Grim hacking cars. And in her spare time, she adds LEDs to thing and hangs out with her dog. So with that, Jaime is going to talk about reverse engineering on hardware.
Thanks, Mike. All right, let me share my screen. Oh, it says that you've disabled it. Can you?
Oh, there we go.
All right. Are you able to see this?
Yeah, we could see it.
Awesome. So, hey everyone, and welcome to my talk, which is an introduction to hardware hacking using a DRM'd LED light therapy mask. All right, got multiple screens, so bear with me. So my name is Jaime. I majored in electrical engineering, worked as an electrical engineer for a little bit, specializing in embedded systems. I kind of accidentally became a generalist software developer, working at a consultancy, and through CTFing, I became a software researcher at Grim. Specifically our team here in Grand Rapids, Michigan, which does cyber physical systems, which is just a fancy word for like automotive, trucking, and industrial system hacking. So been here about a year and a half, had a great time, learned a bunch of stuff. So this particular story is not a work story because I'm typically not allowed to share those for various NDAs. But this story starts quite a while ago, before COVID. So I was at a bar, I was waiting for some friends, and one of my friends texted me about this LED face mask that she had recently bought, and for some reason it had stopped working fairly soon after she bought it. And she asked me if I could help figure out what was going on with it. So I said, sure, sign me up, that sounds like fun. While I was waiting for my friends, I did a little bit of research online. The idea with this mask, which I have kind of partially disassembled right here, is that it has LEDs on this side with red and blue LEDs. Something about it is supposed to help your skin or acne or whatever. I don't know if it works, but that's not the point of this talk. So there's the mask part, and then there's also this kind of remote thing that's called an activator that the mask plugs into. It powers the mask using 4 AA batteries that you can see here. And then it also runs a 10-minute timer. And it fell off, but it used to have a little screen that shows how many uses you have left. And I don't mean how many uses it has left before the batteries run out. I mean how many uses it has left before the device decides to brick itself and it's no longer functional. Like you can't use it at all, even if you swap out the batteries. So what you need to do is go and buy another one for $15 and then add in new batteries, and then you can use your mask again. So you're supposed to use 1 use a month or 1 use a day, so you're going to run out in about a month. And I thought that this was kind of crappy, you know, like you've got this mask that you buy, and it has planned obsolescence to run out within a month, and you have to buy, you know, new electronics. You're throwing away plastic. It's not environmentally friendly. So needless to say, I kind of very quickly got drawn into this project. And this was before I'd ever seen it in person. It is a lot creepier in person. So how to get around this? There's one very obvious way, which is just to short out 2 of the pins and bypass the software entirely. That would have fixed my friend's problem in like 5 minutes. But I wanted to do something that was a little bit more complicated and time consuming and complex. Because I wanted to learn kind of what was going on in the software, and then also have it be a fun, hopefully fun, hardware reverse engineering project. So this product has since been recalled due to eye damage. And by the time I finished this project, kind of working on and off COVID, my friend no longer wanted to use it. So it wasn't practical, but I did learn a lot. And the way that my notes ended up, I felt that it could be a very useful kind of guideline for people who have never done reverse engineering before with hardware and kind of wanted an outline of how to approach it. So this is broken up into a bunch of steps, And step number one is to find something to hack, which seems pretty obvious, but I wanted to cover it anyway. We already talked about what I chose, which was this creepy mask thing. My motivation was to help out my friend, curiosity, things like that. Saving $15 a month would have been nice, but it wasn't the main motivation. And I imagine that saving money isn't going to be a strong motivator for people doing their own hardware projects over something like, curiosity or whatever. So you're probably looking for something else when you're taking apart some kind of IoT or electronic device. You're probably looking for some kind of vulnerability that gives you access that you're not intended to have. And since that involves code execution, we usually think of this as an exercise in software reverse engineering, which Grim also does. But in order to get to that point, you need to do hardware hacking so that you have an understanding of the hardware and how it works together to get to the next step, which is software reverse engineering. In this talk, I only had, or for this project, I only had one copy of the device I was testing. Usually if I'm doing this for work, I get multiple copies. If you're doing a project, like, I don't know, a research project at school, or you're doing something for work, it's nice if you can have multiple copies in case you either break something on accident or you do some kind of experiment and break it on purpose, like if you pull a chip off and dump the contents. But that wasn't always an option, so you kind of gotta work with what you got. So if you aren't given multiple copies or any copies through school or work or whatever, you could do a project like this on your own time. You could either buy a device off the shelf like a normal person, or you can also find quite a few things on eBay. So this is a search for truck ECUs, which is an electronic control unit. Most of these are for engines. But I've also seen a lot of stuff on eBay that probably shouldn't be on eBay. So I guess just be careful with that. Step number 2 is to physically disassemble the thing that you are trying to hack. In this case, I only needed a screwdriver because there are a bunch of little small screws on the front and back, and then the plastic just kind of snapped apart. I don't know how good my webcam is in showing that. So your goal here is to be able to get full access to the PCB inside, be able to see both sides, like pull it out, look at it, stuff like that. If it's a complicated process, take photos. If there's something that plugs in a non-intuitive way, like take a video or something of that, just like help your future self out. But there's also plenty of devices that are not as easy to take apart. For example, if you have automotive equipment or industrial equipment or trucking equipment, it's probably ruggedized because it is used in very harsh environments, like under the hood of a vehicle, for example. So you can still get to the PCB inside, it's just going to be quite a bit more difficult. This is from a video, I think I searched for like removing epoxy, where if you put certain types of epoxy in boiling water, you can then either peel it or chip it away. An example at work, one of my coworkers helped me get a ruggedized case apart using a Sawzall. So this step can be a bit of an adventure. So once you've got the board free and you can see both sides, you've got full access to it. Step 3 is identifying the components, which is a two-part process. But before we get into the details of those steps, I want to talk about reference designators. If you're working as an electrical engineer, or maybe you're an EE and you've taken circuit design classes, then you already know this. But if not, we'll just go through it really quickly. So when PCBs are designed and manufactured, the engineers add markings to the silkscreen layer, which is the white markings on here, or in these photos, I should say, to show where the parts are situated, and then also to identify the parts. This is more for the benefit of humans, assembling and testing things versus, any kind of robotic manufacturing parts of the process. And it's also useful for us when we're trying to reverse engineer and identify things too. There are some boards that are too small to have reference designators because they're just so jam-packed full of components. For example, if you took apart like an iPhone or something, you probably wouldn't see everything nicely labeled. But this board is very sparse, so we've got plenty of room for reference designators. So each one has a letter and a number. The letter corresponds to a certain type of part. For example, C is capacitor, so C8 is presumably the 8th capacitor on this board, unless they did something goofy and messed up their numbering. Resistors are R, connectors use J, and then integrated circuits use U. So of all the types of components on the boards that we're looking at, the U components are going to be the most interesting to us because that's where all of the software and logic and control is implemented. Oh, sorry. So here is a picture of the board taken out, and I didn't label everything on here because it was, I labeled the things that I thought were most important to show for this talk. So you want to identify the microcontroller, any kind of power circuitry, and then look at communication between components, so traces and vias and any kind of connectors, and then communication going outside the board, which doesn't really apply here, but if you had GPIO or serial lines or things like that. So in this diagram, I've got a U reference designator component here, which we're going to get into. I've got a row of resistors. I've got this whole thing is power circuitry, which we'll also get into. Some capacitors. Pretty sure this thing is a microcontroller, which is, I don't know if you can tell, but it's just a blob of epoxy. I've got a button and then a screen. So pretty simple. So getting back to our steps, the first half of identifying the components on the board is taking a whole bunch of photos. So the reference designators told us what type of parts we're looking at. So integrated circuits, capacitors, resistors, etc. Now we want to know exactly what specific part number we're looking at on this board. So we already looked at it, just kind of holding it in our hands. Now we're going to take a whole bunch of photos to get very high resolution images of mostly the integrated circuits, the U reference designator components, or anything else that really strikes you as interesting. So if you can see kind of the very light tan markings on here, this is what we're trying to see in detail. You might be able to see it just like without any help. Maybe I just have bad eyesight, I don't know, but I find it really useful to have a record of all of this. So on here, I've circled all of the U reference designator components on our board. Actually, no, I missed one, which is out of the frame, but it ends up not being important. So I've got the microcontroller, I've got something here at U2 and then U3. So if you have a whole bunch of components, I suggest that you make a spreadsheet. I ended up only having 4, so I just had like a note document. But if you have more than that, then try and be more organized because it will help you out later. So if I zoom in on this component, or actually, I guess it's a different photo, you can see that like the writing on here is actually legible, sort of. ATML H440, 46D1, etc. Kind of like an eye exam. So once you've got that, the second part of this step is just Googling all of these, which I know does not sound very sophisticated, but that's what you need to do. It's a little bit more of an art than a science, and we'll get into how I go about this. But the first part, the HTML, is the brand name. Sometimes you'll have little like logos that you can start recognizing. So you want to know the brand. The next part is usually the part number, or corresponds to the part number, and then the parts after that usually correspond to some kind of variation or batch number. So when you Google these things, don't just put in all of the numbers. Look for Google for numbers SMD, which is surface mount. I can't remember what the D stands for. Or datasheet. So you want to play around with how much of the markings you actually put into your search. So maybe you can leave out atmel. You could just have the H440, add in the variation, leave the variation or batch number out, just play around, and then you'll get a bunch of data sheet results, which is what we're after. We're trying to find the exact part number of each component on the board. And we'll get to why in just a minute. So in this search, it looks like the H440 part is an atmel EEPROM. You can also use smdmark.com, which doesn't always give great results or any results at all, but I think it's usually worth trying. Same thing, you just put in the marking code without SMD or anything, just the marking code by itself, and it will look for any matches. In this case, it looks like this part 7533 is a LDO, which is a low dropout voltage regulator. So next up, you've got some data sheets that you think might be right. It is really important to keep in mind that a lot of these are very similar, or the variations are very similar, and you're going to waste a lot of time and effort if you move ahead with the wrong one. So you want to do some kind of due diligence on the ones that you found to make sure that they probably match. So you don't have to read the whole data sheet right now, but you want to check a couple things to see, if there are inconsistencies between the data sheet and then what your board is actually doing. So the data sheet might list out what the markings are going to be. So it might say that the part is going to have H440 on it, even though the part number is much longer or doesn't have that in it at all. But what I like to do to check these things is to measure the power and ground pins on what I'm trying to investigate. So if it says here that pin 4 is going to be ground and pin 8 is going to be VCC, I will power the board on and then measure those. And if they don't match up, then I know that I don't have the right data sheet. If they do match up, it doesn't mean that I did it right, but if they don't match up, then I'm almost certainly wrong. And then getting this right is going to save you a whole bunch of time later on. So in this case, I thought I had the right data sheet, which is on the left here, but the pins didn't match up. I traced the pins to ground and power on the other components. Those didn't match up either. So I kept looking. I ended up finding a blog post that pointed me to it. It was an end of life kind of uncommon part. So I ended up finding this. This matches. So I feel pretty confident that this data sheet is the right one. All right, so at this point, there's 4 parts that I was trying to identify. I'm pretty sure that I know what 3 of them are. I've got a atmel EEPROM, a Holtec LDO voltage regulator, a CCOS MOSFET, and then I don't actually know what the microcontroller is. And the reason why is because it's covered in epoxy, not epoxy over a plastic component, like the other components we saw had kind of a plastic casing. This epoxy is just over bare silicon. So if I try and take it apart, I risk damaging the silicon. So I wanted to see if I could keep going with this project without identifying it. Usually at work, this is like identifying the microcontroller is like the most important thing that I try to do when I'm starting out. So I would find a way to do it, but because I didn't have multiple devices, I didn't want to tear this board apart and all of the pins and everything were exposed elsewhere. I thought I would just try and move on without it. So for the other components, the LDO and the MOSFET, which are both part of the power circuitry, tells us that the microcontroller and the EEPROM run off of 3.3 volts. Because I was just powering this off of the batteries, that information wasn't that useful, but if I was doing something like powering just part of the board, that would have been nice to know. I've pretty much ignored the display because it's not storing any information. So I want to focus on the double EEPROM first. All right, so step number 4 is more data sheets. Very exciting, I know. So you still need a DMM. You probably want some coffee because this is going to take a while. You already read them to see if they fit, and now we're going to read them to actually learn about the components and how they work in depth. So we started out looking at the board. We had all of the components on there. We narrowed it down to the U reference designator components. And then we narrowed that list down further. For example, we decided that the LDO wasn't that important, that the MOSFET wasn't that important. So we've narrowed it down to the things that we think are the most interesting in terms of, a security perspective, like interesting in terms of the information they can give us or some kind of control or access that they can provide. And you want to do the same thing on whatever board you're trying to take apart, because you need to prioritize your time and focus in on the things that are most likely to get you some kind of interesting result. So for each of these, you want to read about the different parts as much as possible. For example, what is the overall purpose of the component? Can you summarize what it does within the context of the board? How does it communicate? What is it communicating to? Is it sending information to other components? Is it some kind of wireless part that is broadcasting information to other products outside the board? What information is it sending? Is that interesting to us? Do we care? Like, do we want to go after that information? Ask if it has security features on it. Are there any measurable pins that determine what setting it might be in? What are the levels on those pins? For example, if you had a write protect pin, that would be nice to know. And then is there any other kind of just general interesting information that we need to know about a given part? So in this simplified example where I'm just looking at the double EEPROM part, it turns out there is an instruction set in order to communicate with it. And this is information I found in the data sheet. I added it to my notes. I need to understand how this works and then use this to craft the messages that I'm going to be sending later. So trying to figure out how all of these things work together might be difficult if your board is more complex or has inner layers or ball grid array parts or things like that. So you might have to get creative, but you can usually find a way to measure things if you study the board. So in the case of this very simple board, I could probably reconstruct the entire circuit diagram, but I don't really need to. And like I said, in most cases, it's probably not feasible. So instead, I want to draw a block diagram that kind of summarizes like conceptually what's going on and any interesting things that I found so far. And this is a really useful skill for kind of in a work context where I have to I usually have multiple people on the project. I want to be able to communicate what I found in a, understandable high level way. But if you're working by yourself, it's also useful just because you might forget. You might have to like put the project on pause for a little bit and come back. So I draw a block diagram of the power, like how the board is powered, what parts are talking to each other. Is there memory separate from the microcontroller? Where is the logic implemented? So microcontrollers as the main example, and then specialized areas like CAN, transceivers, or antennas, or things like that, which does not apply to this board. You don't have to understand all of this to a double E level. If you do, like, that's great. But if you don't have an electrical engineering background, don't let that trip you up too much. You don't need to, for example, you don't need to understand everything that's going on in the power circuitry. You just have to understand, like, we're going from 5 volts to 3.3 volts. So, like, try to learn the things, like, try to dig into where you have gaps, but don't let it stop you from trying to dig into this. So if we zoom back out to our goal of trying to modify this whole mask thing so my friend can use it again, I want to try and modify the number of uses left because it had counted down to 0, so I want to re-up that somehow. So my plan of attack, I think, is going to be the double EEPROM. I know that it's there for a reason. They would have not added it in if it didn't do anything. There's not a whole lot else going on this board, so I think I can assume that the microcontroller is storing its count in the memory, or in this kind of off, in this separate memory chip. So for my data sheet, I identified which specific pins on the double EEPROM are used to talk to the microcontroller. So I have these 4 here in my diagram. So kind of getting ahead of myself here. We're getting to the fun part, which is actually starting to get access with the different components on the board. So we need a couple more tools for this step. We talked about protocols just now. We need to use that to determine our strategy for how we're going to get access to the board. We know what's going on. We've identified everything on there. So now let's think about how we might gain access through the different methods of communication that we just talked about. Now that I'm saying that, I think I left out that this double EEPROM chip uses, this is an instruction set using 3-wire SPI. So we narrowed down our list of components to the 2 that might have some effect on the function of the board. The microcontroller is covered in epoxy, so we kind of eliminated that. To re-enable the functionality of the activator, I decided that I'm going to try and find where the number of uses left count is, and then modify that somehow. So because I have easy physical access to the double EEPROM, it's out in the open, because I know how to communicate to it, and because I think it has what I want, this is what I'm going to prioritize first. If this was a different board, you look for different communication methods on the chip. So maybe in your data sheets that you saw before, maybe 2 parts are talking to each other via SPI or I2C or something like that. Maybe there is a serial line for debugging. So another project that I've done recently is this camera, and I don't know if you can see it in here, but there are 3 header pins that I've attached wires to, and these turned out to be RX, TX, and ground, which was a method of debugging that the engineers left open. So I was able to connect to that, open up a COM port on my computer, and then have interactive access with a microcontroller on that board. So the reason why these methods exist is because engineers need some kind of debugging access to modify things, to test things out in the field. You're supposed to lock these things down in production in a way that's not easily reversible, but that doesn't always happen. JTAG is another example. If it is locked down, you might be able to find a flaw in the security of how they're doing that and then still find your way in. For example, glitching or using glitching. So from this step, like I have one plan for how to get access, but if you have another board, you probably have a whole list of things based on different communication methods and different debugging methods. So the reason, so you probably noticed that what I've been describing is sounds like a lot of engineering, and it is. It's you trying to think like an engineer and try and figure out how they design this and how they might have given themselves a way to debug things, and then taking advantage of that so that you can get access to. So back to our board, I want to communicate with a double EEPROM. I need some kind of special tool to do this that that has the ability to use to communicate over a 3-wire SPI. There are a bunch of tools that do this. One example is a bus pirate, which is about $20. You can get it off of like SparkFun and things like that. There's other tools that you can use, and this is decided based on the communication protocols that are on the board that you're trying to access. I've got a link at the end that I think will be helpful. Once you've identified, like, okay, my board has this, you can look at this GitHub repo and kind of find tools that are specific to that protocol. So the end goal on most of these devices or most projects is code execution. That's not true in my case, but like I said, you have all these different methods of communication. If a component is communicating with other components or with the outside world, there's no reason that you can't possibly, you might be able to get in between and kind of gain access or information that way. So like I said, make a list, try and prioritize it by likelihood, the cost of tools, you know, familiarity, things like that, and just work your way down. So in my case, I wanted to look at the double EEPROM and hopefully be able to change the count. So I know the chip, I know the specific pins that I want to use. I soldered leads on, which is before I got smart and used one of these chip clip things. I don't want to go into the specific settings for Bus Pirate. I have a blog post written about how I set that up. But what I wanted to do is read just everything in the double EEPROM. I just wanted to dump all of the memory out and see if I couldn't make sense of what was there. So I looked at the data sheet. I knew how to send a read command to the double EEPROM. So I'll show that in the next step. And what I got back was a whole bunch of bytes that were all FF, or all Fs, I should say, except for 4 that were different values. And of those 4, 2 of them were either 0 or close to 0. I think it was like 0 and 1. So I thought that because the display was showing a 0, that probably meant that those 2 values were somehow storing the count. So this is what the Bus Pirate command for writing, or for reading, I should say, from location hex 50 looks like. And then once I knew what those, once I saw the 0 and the 1, I wanted to try and change that to a different value. I think I started out writing a smaller value to it, but I looked at the data sheet again. I had the instruction set that I had learned. So this first command here is disabling the write protect, and then I'm sending a write message to change the value of location hex 50 to 98. The value of 55 to 99, and then write protecting it again. And success, I was able to change the value to 98, and then the mask worked again. So I kind of got lucky that the first thing I tried and the only option that I tried happened to work. I mean, after a lot of debugging, it didn't work right away, but if it doesn't work for you and you've got your list of things, just work, try the next thing and keep going, and something will eventually work. So at this point, I was feeling pretty good about my progress. I got it working. The mask worked again. I could have given it to my friend, although at that point, I think it got recalled. So, it was a little bit of a hollow victory. But then I made some more changes because I wanted to see, like, if I could get it higher than 99 through, if it's a hex representation, then I should be able to get it higher. I ended up in a weird error state. The display read dash dash, and I just like could not get it working again. The mask wouldn't turn on. I programmed it again with the last known good state. It still didn't work. I read through a bunch of Neutrogena documentation, which was like completely thrilling, because I wanted to try and reset the device, but that didn't work out either. I pulled out the batteries. I did the whole like turn it off, turn it back on thing. That didn't work. What ended up being the issue is that this capacitor here was still charged up, as it takes like 5 minutes to discharge apparently, and I wasn't waiting long enough. So as a result, the double EEPROM never actually fully powered down, and neither did the microcontroller, and it was still working off of the previous error state. And I realized that by taking out my DMM and measuring it. I took the batteries out, I shorted the capacitor, and then after that, I was back in business. So the point of this isn't just to like share my moment of panic and complain about this. It's to point out some ideas that I think will be useful. So far, I've been talking about how the individual components work and maybe how they work in small groups, but you also need to think about how the thing you're taking apart works as like a consumer product. And you can benefit from finding like documentation or guides that allow you to interact with the thing at a consumer product level instead of just looking at each individual chip. You have to kind of zoom out sometimes and see the whole picture. Once you get something working, you always need to write down what you did and like in as much detail as possible. If this applies to you, try and find ways of having a known good state that you can revert to. Like maybe you copy off all the files from a microcontroller when you first get access, so that anything you do after that you can like revert to a known good state. And then for electrical things, prove things out with a DMM. You know, I knew at a conceptual level that powering down boards with capacitors on them, you know, they don't power down instantaneously, but you know, sometimes you forget. Sometimes, like me, I'm just impatient, I guess. Hardware really only cares about the physical reality of its state, so you need to measure and be sure. Alrighty, so at this point, we're able to alter the double EEPROM. We got the mask working. You know, it functions like a new product at this point. So what should I do next? I've got an idea it uses. Not that my friend is using this now, because obviously I still have it. But if you're using it once a day, that would only get me like 3 months before I have to get this whole setup out again and reprogram it. So I want to think like, is there something I can do to permanently bypass this and not have to deal with it again? And that's what I mean by persistence. It's a concept that applies to hardware hacking and embedded systems projects in general. If you need to do some kind of error-prone, difficult, or potentially damaging thing to a board or a product every time you need to get access, you want to look for ways that you don't have to do that in the future. You know, so that you don't have to keep jumping through all these hoops. You can just focus on the software part from here on out. So that might look like adding your own username or password. First, you know, something more complicated than this. Maybe you re-enable a method of communication that had been disabled for production. Maybe you use the access that you have to get other access that's more interesting or more helpful, and so on. So I don't have as many options here, and I didn't actually get this working, which is kind of a bummer for this talk, but I did try a bunch of things. So if there was a write protect pin that I could have enabled, then the microcontroller would try and update the value and it wouldn't work, or the update wouldn't take. So I would just be at 98 uses forever, but this chip doesn't have one of those pins. It's all done in software. I tried to cause logic errors by swapping values in memory, and that just kind of got me in a world of hurt and didn't work. I could have tried to do a software write protect, but because each of the microcontroller commands are bookended with write enable and write disable, my that idea wouldn't really help. I tried shorting out some of the other lines to see if I could cause hardware failure states that that the software wasn't anticipating. I tried to change the other EEPROM values, which didn't really help. And I could have tried to figure out what the microcontroller was under all of that epoxy, you know, identify it, learn how to reprogram it, maybe replace it. But if I was going to start doing modifications like that on the board, I could have just done the jumper that I thought about originally. So I just decided I'd reached my educational goal. I'm going to chalk this up to a win and then work on a different side project. So to recap, if you're trying to do this with another board, you want to find something to hack, see if you can get multiple copies of it, physically disassemble it and get access to both sides of the PCB. You want to identify what's on the board all the way down to the specific part number by using photos and then Googling for the SMD markings. You want to read the data sheets and then understand how they work and how they interact with each other. You want to come up with a plan of attack, or actually really plans of attack, and then kind of prioritize them and work through them. Hopefully establish communication and then avoid the pit of despair by taking good notes and helping your future self out. See if you can't establish persistence, and then you get to do some software reverse engineering. So if you walk away from this talk with nothing else, remember to take a lot of notes and try and get things right early on in the kind of research, more tedious stages, so that the later stages can be more enjoyable. All right, so to end with some resources, there is the Hardware Hacking Village at DEF CON. DEF CON just announced that it's going to be partially remote, partially in person. So I don't know what Hardware Hacking Village is going to do with that setup, but you might be able to attend some things virtually and learn more there. This is the GitHub link that I was talking about with the kind of glossary of different things to do for various protocols or board features. There's a book called The Hardware Hacker by Bunny Wang that it's kind of autobiographical, but it's also interesting from a hardware hacking perspective. Grand Idea Studio has a whole bunch of really great resources. If you do your own electronic projects, you know, either on your own time or for school or work or whatever, that is also helpful because it's easy to, or it's easier, I shouldn't say it's easy, to reverse engineer things that you've helped engineer like in a normal sense. And then, you know, just find some random pieces of hardware around your house and see if you can't try out some of these ideas. So anyway, thank you for watching. If you have any questions or you want feedback on something or just anything, feel free to email me or DM me, probably email. I've tried to avoid Twitter lately. But anyway, I hope you enjoyed this talk and thank you for watching.